Hello, everyone. I would like to, first of all, I would like to thank you very much, Karl Landsteiner, for accepting our invitation. He's from Institute of the Theoretical Physics in Madrid. And I think no need to say that he's expertise in many areas in high energy physics. And he will gonna talk about quantum anomalies in matter today.
Okay, yeah, thank you for this kind invitation to give the seminar in your seminar series. Yeah, so I will talk about work I've been doing over the last decade or so on the effects of anomalies, quantum field theoretical anomalies in matter. There are a couple of reviews which I've co-authored over the years, which are here on the first slide. A recent one with Maxime, also from Tour, and Iago Ferreros, Adolfo Krushin, and Maria Vosmediano. Okay, so that's the outline of my talk. I will start with reviewing a little bit what an anomaly is in quantum field theory, especially in the quantum field theory of chiral fermions. And then I will promote this idea that one can use Chern-Simons forms as effective actions for the anomalies, and I will discuss several applications of that. For example, the quantum anomalous Hall effect. I will discuss the chiral magnetic and chiral separation effect and the chiral vortical effect, and how these effects can be understood from an effective action point of view based on Chern-Simons forms. And so also it sort of leads to this sort of conjecture that what I would call topological quantum matter can be understood as putting as Chern-Simons forms as effective actions actually on black hole metrics, on metrics which contain some sort of black hole. I will explain, hopefully be able to explain this in more detail. And then I will discuss some applications. And I just noticed I missed here one of the applications. So I just have the wild condensed matter application of this here, but I will also very briefly talk about the possible application in high energy physics. Okay, so if you Google for quantum anomalies, this is one of the pictures you find. So it's quite frightening. Yeah. But happily, there are also other things. So this is called anomaly quantique. And the good news is there are survivors to it. So that's a positive outlook for this seminar. So you can survive it. Okay, let me go on and discuss the quantum theory of chiral fermions. Let's start with something very, very straightforward, the Massless Dirac equation. So which is just a spinor. It's actually a four-dimensional spinor here. And it's annihilated by acting with this Dirac operator on the spinor. And what you can do is you can define this chiral generator, gamma 5, as the product of the gamma matrices, gamma naught, gamma 1, gamma 2, gamma 3. And then you can define independent left and right-handed components just through the eigenvalues of this gamma 5 operator. So they are called then left and right-handed Weil spinors, these projected spinors. And they fulfill a very, very simple equation, which is written down here. This, we're going to call it the Weil equation or the Weil Hamiltonian. And it's basically just the Pauli matrices, the inner product of the Pauli matrices with the momentum or the momentum wave number, inverse wave number. Okay. And there can be a plus and minus sign, and this plus and minus sign just there's a one-to-one correspondence with the chirality eigenvalues here, this gamma 5. So, and this gives a very nice physical interpretation of what this chirality means in the case of massless spinors. It means that the positive energy eigenstates are such that, say, for the plus sign, the spin measured by sigma is aligned with the momentum, whereas for the negative energy eigenstates, the negative chirality states, the spin is anti-aligned with the momentum to get a positive energy. Of course, in reality, you have positive, negative energy states, and the spectrum forms what is called a Weil cone, which I've shown here in this picture. So you have this spin momentum locking for chiral fermions, and you can see picture here, you have a chiral fermion which rotates in one direction. If it goes, say, to the right, actually, I think I got it right. It also rotates in the right hand sense. Okay, now what's the anomaly? So when you have such the spectrum of a chiral fermion in a strong magnetic field, then the spectrum organizes in what are called Landau levels. So there are, I've depicted here the energy levels. There are, of course, infinitely many of them. These are positive energy states. And since it's a relativistic theory, there are also negative energy states. And then what we do in quantum field theory is we imagine all these states to be populated such that no, say, electron which sits up in this excited state could fall down. And then, so unfortunately, the movie is already running. I thought that the movie will run when I click on it, but it runs already. So there's this one special Landau level where the momentum here now, the momentum just extends just along the magnetic field. It's not anymore a three-dimensional momentum, but just a one-dimensional momentum. And this lowest Landau level has this property that it's chiral, which means the positive energy states have only positive momentum, and the negative energy states have negative momentum. So if we start out with a description in the vacuum, we would say, okay, yes, this was the vacuum. Then the states are filled up to this point, which we call the normal ordered vacuum, right? So we perform a normal ordering prescription, which basically subtracts all the contributions from these occupied states below the normal ordered vacuum. But then what's happening when you, in addition to the magnetic field, you also switch on an electric field, then the electric field, of course, exerts a force on the electrons or on these fermions, and it will try to accelerate these fermions. Now, I can't do anything to these states because these states here are completely occupied. This in this actually lowest Landau levels, the negative energy states, they are completely occupied. There is no, and due to Pauli blocking, these electrons cannot move over here or anything like this. They're just completely static. But in the lowest Landau level, the electric field can actually do some work and push energy into the system. But of course, if you push energy into the system, you also have to necessarily increase the momentum of this state. So what will happen is you take this infinite Dirac sea in the lowest Landau level and push it to the right, which means that now states which formerly you thought are below the vacuum now are pushed out of the vacuum, and the whole effect looks for a quantum field theorist who is introducing a normal ordered vacuum like particle creation out of the vacuum, out of nothing. And so you can apply a simple counting rule and you find that the number of states that are created in parallel electric and magnetic fields per unit time is given by this formula. And that's a very physical picture of what the anomaly does for chiral fermions. Okay, now that was very simple. Here's a little bit more complicated formula, which shows the so-called triangle anomalies in full glory. So here I imagine I have some theory containing chiral fermions, and there are currents like this. So QA is a generator, generates some symmetry, and Q mu A is the corresponding fermion current corresponding to that symmetry. For example, in a Dirac fermion, the axial symmetry, which would be just where the QA is this gamma 5 operator. And then you can calculate the anomalies, the F mu nu, F rho lambda with contracted with epsilon tensor is just a relativistic version of E in B. And then depending on the quantum numbers of the different symmetries, which are measured here by these charges, QA, or by method here, you find these so-called anomaly coefficients. And so it's very simple for this triangular anomaly containing only these gauge fields. The corresponding anomaly coefficient is denoted as dAbc and is given by the sum over the charges of the right-handed fermions, the triple product over the charges of the right-handed fermions, minus the triple product of the charges of the left-handed fermions. And quantum field theoretically, this product appears when you calculate this triangle diagram of three such classically conserved currents. So classically, there should be a zero on the right-hand side, but quantum mechanically, there's an obstruction of defining the quantum theory in such a way that all these currents are simultaneously conserved. So this is the usual anomaly, and there's a second form of anomaly, which was also, so the first one is the famous Adler-Bell and Tokiev anomaly. But already in 1969, in the same year, Kimura wrote a somewhat less known paper where he showed that there's a second form of anomaly where you take one current here and you take two energy momentum tensors here, and the natural gauge fields they couple to is the metric, and therefore you find this, if you express this as a field strength, similarity to the field strength of the gauge fields, the natural field strength is the curvature, Riemann curvature. So you find here a term which contains two Riemann curvatures. And there's also an anomaly coefficient, BA, which this time is simply the sum over the charges of the right-handed fermions minus the charges of the left-handed fermions. So it's important to emphasize here that this is a statement about the operators in the quantum theory of containing chiral fermions. It's completely independent of the state. So I've written here an expectation value, but I've not told you which state this is. So this equation is really true in all states of the theory. And it's topological in various ways. So here, for example, these terms which appear here, they are really topological densities, Pontryagin number, Chern numbers. But it's also topological in a field theoretical sense, namely it's really independent of continuous deformations of the couplings of the quantum field theory. So you can actually calculate this triangular anomaly in the completely free theory, where you just define these composite operators, psi bar psi, and then with the charges put in there, and then calculate this triangle diagram without having any internal lines. And there's a theorem due to Adler and Bardeen, which tells you that interactions which include internal lines here, which decorate this basic one-loop triangle diagram by internal lines, do not renormalize these results. So in this sense, it's a quantum field theoretical topological result. And therefore, it's so easy to calculate and know if there are anomalies or not. You just have to calculate these anomaly coefficients. Okay. Another thing, yes, okay, which I want to emphasize is that sometimes it is said or thought that the anomaly is absent if you don't have these external gauge fields. So for example, in the simplest case, this would just be an parallel electric and magnetic fields. But even if there are no electric and magnetic fields, the statement that the theory has an anomaly is really a statement about the full quantum theory. And you can never get rid of it by just switching off some external fields. The anomaly then, if you don't have any of these external fields, and if you live in flat space, for example, the anomaly then shows up in correlation functions like this one with triangle diagrams. So you would expect for a classically conserved current that if you insert the operator d mu j mu into correlation functions, that this correlation function gets annihilated because naively d mu j mu is equal to 0. But in fact, in this particular triangle diagrams of three-point correlation functions, there are non-removable contact terms, which are precisely the anomalies. So the anomaly is always present. It's an integral property of the quantum theory, even in flat space and even in the absence of external gauge fields. The anomaly is still there in the quantum field theory of chiral fermions. Okay, so that was a basic review of triangular anomalies. And So here, for example, for a single chiral fermion, we had this result that it's E in B, parallel E and B fields. Now I will quickly switch to form language here. So F is the field strength tensor, F mu times dx mu dx nu. It's a two-form exterior derivative of the gauge field. And so the anomaly then can be written as the integral of this Chern number, if you want. So that's a local expression in the fields, a local expression in the gauge fields, which coupled to this classically conserved currents. And it's important that in the effective action, the anomaly appears as a gauge variation of the effective action. So if the theory would be anomaly free, then the effective action would be invariant under gauge transformation. But if it has an anomaly, then it picks up this non-vanishing term. And C you can think of as being the gauge parameter. Now, this cannot be by itself written as a gauge variation of a local form in configuration space. You would have to write it as some non-local form. Here, for example, there's a non-local form which contains the box operator. Of course, there's a non-local Green's function. To my knowledge, the first one who wrote this down was Krasnodar in 1984. And when you do a gauge transformation here on this gauge field, then this is dA. So you generate here a box operator that will cancel with this box operator. And you just generate the FHF term. Now, locally, you get a delta function. You can do one integration and you go back to a local form. So in the effective action in 4 dimensions, there's no local way of expressing the anomaly. But there is a local way if you go to one higher dimension. And this is by the means of what are called Chern-Simons terms. And for example, here's a simple such Chern-Simons term, just gauge field, wedge F, wedge F. So now this is a 5 form, and I can integrate it over a 5-dimensional manifold, which for the moment I don't want to specify too much, but I just want to say that the space-time that actually interests me, on which the quantum field theory lives, the quantum field theory that has an anomaly, is the boundary of the manifold where I integrate this 5 form over. And if I do now a gauge variation, so I take A and vary it to, say, dc, with C being the gauge parameter, then this whole thing is a total derivative, and it means the integral just evaluates on the boundary, and then I identify the boundary with the physical spacetime, and I recover the anomaly. So that's important for the following. The anomaly can be written as a local form if you go to one higher dimension. And there is a very nice, beautiful theory to it, developed by Storan and Zumina in the mid-80s, going under the name of descent equations, etc. So if you're interested in that, I recommend reading the papers of Storan and Zumina at around the mid-80s. Okay, so one application of this is in condensed matter physics, the theory of the quantum Hall effect, anomalous quantum Hall effect, where you imagine you have what is called a Chern insulator. That's a sophisticated material. It's a planar material, so basically 2-dimensional, 2 space dimensions. In our relativistic speak, it would be 2 + 1 or 3 dimensions, but in condensed matter, we count only space dimensions. And in a solid, the electrons occupy so-called energy bands, and some of these energy bands, they can have topologically non-trivial structure, which gives rise to the effective action. So what happens is that's an insulator, which means there are no local degrees of freedom in the bulk of this material, but the topological structure of the relevant band in the insulator is non-trivial, and this gives rise to a non-trivial effective action. But since there are no local degrees of freedom, the effective action has to be some sort of topological action. And basically in 2 + 1 dimensions, there's only one such candidate, which is basically this Chern-Simons form. And then again, if you do a gauge variation of this Chern-Simons form, it's okay in the bulk, but on the boundaries of this material, of such a material, you would get an anomaly, because it's of course not gauge invariant if you evaluate it on the boundary. becomes a total derivative, and you get only boundary contributions. And in order to restore gauge invariance, which is sort of the most sacred principle in physics we really know, gauge invariance, say for electromagnetism, should be absolutely implemented, should never be violated. That tells you that on the boundary, something else must happen in order to cancel this anomaly. And in fact, what's happening is that there are so-called edge states on the boundary of such a material, which by themselves are chiral fermions, and they have a non-local effective action. And these chiral fermions on the boundary have an anomaly which precisely cancels the anomaly you pick up from the variation of this Chern-Simons term, such that the effective total anomaly vanishes on each of the two boundaries. Right? So there's an interplay between this local form of the Chern-Simons action, which now lives in 2+1 dimensions, and the non-local effective action of a massless degree of freedom, which lives on the boundary. So here it's important to remember that this is an insulator. There are no local degrees of freedom. It's really sort of vacuum here, a topologically non-trivial vacuum, because that's still this Chern-Simons term. But here you really have massless matter. So, and when you have massless matter, you can describe it. States in equilibrium, they are described by chemical potentials and temperatures. And it's known, for example, that if you have such a right-handed fermion in one dimension, in 1+1 dimensions, and you put it at finite chemical potential, then you generate a right-handed current. And that's easy to understand because as you populate the states, the chiral fermions have no other degree of freedom but just to move along this edge. Since they're chiral, they do not have the degree of freedom of going backwards. They are extremely stupid and stubborn. They only go in one direction. And of course, if I have a fermion that moves in this direction, it generates a current, and the current and the chemical potential just measures how many electrons or fermions are moving along the edge. And the same, of course, on the left-hand side for the left-handed fermions going down. And so what's interesting is that the number, this current here, is also related to the anomaly, which I will argue now. So this I said already, so there are sort of two sorts of currents which play a role here. There is this bulk current coming from the Chern-Simons term, but there is also this edge current, and this edge current depends on a state parameter of the edge theory. Namely, it depends on the chemical potential. It depends on how many of the available states you have actually filled. And the question is,
can you ask something?
Yeah.
About the previous slide?
Yeah.
But here, they don't cancel each other because maybe there is some chirality imbalance in the system. If the right-handed electrons is equal to left-handed electrons, they can cancel each other. But in this case,
that's true. So what you actually cancel, and this is the whole theme of the talk, is the anomalies cancel. So because here locally the anomaly of this chiral fermion cancels with what is called anomaly inflow from the Chern-Simons term, and on this side as well. But the currents do not necessarily cancel, because it is perfectly fine to have a state in which these fermions here are at a different chemical potential from those fermions. And then you will get a net current.
Mm-hmm.
But the anomalies still cancel. So mu is a parameter that describes the state of the system, whereas the anomaly is something which characterizes the theory by itself. But every quantum field theory, every quantum system, the theory can have many, many different states. And here, this is a particular state where you are in equilibrium or very near equilibrium, such that the state can be described by a chemical potential.
Okay.
Does this answer the question?
Yes. Thank you.
Okay. Thanks. Okay. So what I want to argue now, that even the state-dependent currents can be described and understood by Chern-Simons theory. So I want to argue that what concerns anomalies and these currents which are related to the anomalies, they are can be described again by Chern-Simons actions. Chern-Simons action where I invent myself an appropriate 5-dimensional or 3-dimensional manifold which incorporates the important features that tell you in which state your theory is. Okay, so in particular, I'm interested now in states which are equilibrium states, which means they can be described by parameters which are finite chemical potential and finite temperature. And now I have to think about how can I encode, say, the information that my theory is at finite temperature. It has an anomaly and it is at finite temperature. And this I want to encode somehow in an effective theory. So let me do this for the probably already most complicated example, the gravitational type of anomaly. So there is also a Chern-Simons term, and it has this structure. There is a gauge field, and there is this wedge product of the curvature tensors. And this is supposed to be a 5-dimensional manifold. So if I do a gauge transformation on this gauge field, I get a total derivative again, and it's evaluated on the boundary. So I want the boundary of this manifold to be the 4-dimensional real Minkowski space. And so now I have a candidate for an effective action, which describes the anomaly of the 4-dimensional theory. Okay, and now I want to say, what are the properties of this 5-dimensional manifold such that I can encode the information that the theory is at finite temperature. Okay. And now, how do we encode the information? Of course, here I have a Riemann, the product of Riemann tensors. So somehow the information about temperature must be encoded in the geometry of this 5-dimensional space. And okay, we all know since the 1970s from the studies of Hawking that there is in fact a geometry which naturally encodes the information of temperature in the geometry, and that's a black hole geometry. So here I've written down a typical black hole geometry. R is just, say, the coordinate in the 5th dimension. T and X are the coordinates of your 4-dimensional Minkowski space. F and G are some functions, which for the moment, I just want these functions to be one on the boundary. And then what I do in addition, I make this a slowly rotating black hole, which I have to do for this 4-dimensional anomaly. It should be slowly rotating. I introduce what is called the gravitomagnetic field, and the angular momentum actually can then be calculated as the curl of this gravitomagnetic field. Okay, and then how is the temperature encoded in this geometry? Well, you demand that this is a black hole, which means that there's some interior point at r equals 0. This factor in front of dt squared vanishes. And at the same time, the derivative at this point is given by 4pt. So that's you can view this in several ways. So for example, starting from a generic black hole geometry, you can show that if you put a quantum field theory in such a geometry and you go very far away from this, the quantum field theory finds itself at exposed to a thermal bath of Hawking radiation at this temperature. So that's the famous result of Hawking, that the temperature of a black hole is given by what is called in gravity, from just the geometrical point of view, the surface gravity. A sort of fast way to see this is to go to your Euclidean section. For this, imagine that there's no such rotation, and you just take t to it such that you get a Euclidean signature. Then at f equals 0, this time shrinks to 0 size. And for this to be a regular geometry without any singularity, it means that this Euclidean time coordinate has to have the topology of a circle. It has to be identified with a period, which is given by precisely the derivative of the f function at the origin, or at what is then the horizon. And so this regularity condition on this geometry then also fixes the temperature, because the periodicity, a quantum field theory at finite temperature can be viewed as quantum field theory in Euclidean space-time, with the time being identified and the periodicity being just the inverse temperature. So there are several ways of seeing this. It's sort of a standard result of black hole physics, that the derivative of the so-called blackening factor at the location of the horizon gives you the temperature up to some factors of pi. In addition, there are some technicalities. I really only want the intrinsic curvature at the boundary. So this means the derivative on the boundary of this function should vanish. And then I say, okay, let me choose this and calculate how much current do I get. Well, I know how to calculate a current from an effective action. I just look at the coefficient of the gauge field, and that's the current. So now I introduce a gauge field, which is just a constant gauge field all over the black hole geometry. So if there would be no anomaly, a constant gauge field would be just trivial and would not have any effect. But because of the anomaly here and because of this Chern-Simons term, now I can pull the constant gauge field outside, forget about it, and just integrate the rest and interpret it as a current. And so if you plug this geometry into this R wedge R term, it turns out that it goes into this integral. That's a boundary term by itself. And with these boundary conditions, it just becomes this expression. It's temperature squared times this rotation parameter times a factor of pi's and the anomaly coefficient. So what this tells you, this way of effective description of chiral fermions, of this gravitational anomaly of chiral fermions, is that if you heat up a theory in 4 dimensions of containing chiral fermions, which has this gravitational anomaly, and at the same time you subject it to a slow rotation, there will be a current which flows along the rotation axis and is proportional. So Bg is the angular momentum, and will be proportional to temperature squared. Okay. So here's the obligatory picture of the Event Horizon Telescope showing a black hole. Of course, my black hole is not the real physical black hole. It's just an effective description of the chiral anomaly, of the effects of chiral anomaly for the finite temperature quantum field theory. Okay, the same thing you can do with the chemical potential, but now you have to encode the information that the theory is at chemical potential. You don't encode it into the geometry, you encode it in the field configuration for the gauge field. So here, for example, I've written the corresponding Chern-Simons term for the axial anomaly, which is an anomaly. So A is a current, is a gauge field which couples to the axial current. So that's the current that calculates the number, measures the number of left-handed fermions, right-handed fermions minus the number of left-handed fermions. So this corresponding gauge field I call A. And V you can think of as the usual gauge field for electromagnetic gauge field, or just the gauge field that counts the sum of left and right, or the gauge field that couples to the current, which counts the sum of left and right-handed fermions. That's the Chern-Simons expression for the original APG anomaly. And again, you can go through the same arguments. Again, basically, of course, now to speak of a black hole is too much because it's even insensitive of the geometry. It's just sensitive to certain boundary conditions on these fields, but you can argue just on general principles what these boundary conditions shall be. And also you switch on a background magnetic field in order in this in the 4-dimensional theory. And the Bianchi identity tells you that it's in this additional direction, this in direction which I've invented myself here. The magnetic, this magnetic field is just a constant in that direction due to Bianchi identity. Then again, you can evaluate this effective action and you find this expression for the chiral current in the presence of a chemical potential and a magnetic field. And again, it's completely determined by this anomaly coefficient. You can also do something else. You can invent an axial chemical potential, which means now, this is precisely what Ada said, that would describe a situation where you have more right-handed fermions than left-handed fermions. Then you would describe this by what is called an axial chemical potential. And you also can encode this in this field configuration and evaluate again the effective action. The only difference now is that you want to calculate now the current, not the axial current, and the current couples to the V field, but the V field doesn't appear explicitly, it only appears in the field strength. So in order to get the variation with respect to the V field, I have to do some partial integration, and in this partial integration, I pick up some additional surface terms. And now there's a very nice structure which is very important in the theory of anomalies. There's one term to this current, which depends only on completely covariant expressions, meaning on field strengths of gauge fields, like FA, field strength of the axial gauge field, and field strength of the vectorial gauge field. And then there's a term which pulls back on the boundary. So for this, I don't need to know anything. Here, for this guy, to evaluate this guy, I have to make some assumptions about how these field configurations look like on the 5-dimensional space. I can nail it down if I say this is an equilibrium field configuration. This should describe an equilibrium field configuration with interpretable as the theory being at finite chemical potential. But this is completely independent of it, of any state, of any information of the 5th dimension. But both terms contribute to the current, such that the actual expression you get is this one. Again, there's the anomaly coefficient. There is the chemical potential, which measures if you have more left-handed and right-handed fermions. And there's the temporal component of this axial gauge field. And if the two happen to be exactly equal, then they actually cancel, and you get the 0 result. And so that harks back to something which is known as so-called second Bloch theorem, which says that you cannot have an expectation value in equilibrium of an exactly conserved current. So in this theory, the actual, say, electric current has to be, it's always exactly conserved because the electromagnetic gauge symmetry is never broken. And that means, and indeed that comes out from this little calculation, that the field configuration, which explicitly describes equilibrium without any strict equilibrium, is such that these two terms cancel precisely, and you get vanishing, what is called chiromagnetic effect in equilibrium. Fortunately, in the early times, in many of these calculations, people just calculated the first part, sometimes also only the second part, but a careful consideration of this effect shows that there are these two terms that contribute, and you need to take both into account. Okay. Now that's a very abstract way of talking about these effects. A much simpler way is when you go to a concrete model, like just chiral fermions in the magnetic field. So here, for example, we are back to our chiral fermion in the magnetic field and the Landau level picture. Here's the lowest Landau level. And now I imagine I'm not in vacuum. So now not only the states until here are filled, and of course I subtract the vacuum by normal ordering, but now imagine that the states are filled up to some level of chemical potential mu. And then I can calculate what is the current. Now, from these higher levels, there will be no current because it's completely symmetric, and you can do this integral and get 0. Of course, as I said, they cannot move. But the lowest Landau level, you see, you integrate from here to there, from 0. Well, actually, then I also allow for finite temperature. So that means that high energy states, which are above mu, they are exponentially suppressed. And then you have whole states, which you reinterpret as antiparticles. So they come with a minus sign here. And you just count with these Fermi-Dirac distributions for the particles and the antiparticles. How many guys are there in the lowest Landau level? And so since the electron, the positive energy states, they move in this one, and the holes, they move in the opposite direction. They both give the same contribution to the current. And this integral, actually, you can do exactly, and it's a temperature-independent result, and it just picks up the chemical potential. So this is a very simple way of calculating this. And there is no real, it's not explicit here that this depends somehow on the anomaly. But if you do this calculation more carefully and you check really what are the quantum numbers that go into the calculation of this, you will see that in front of this mu coefficient, there precisely this anomaly coefficient, DABC. Okay, so here again, to summarize the theoretical part of my talk, these are the formulas for the anomalies. So that's the usual anomaly, this gravitational part of the anomaly coefficients. And here are these anomaly-induced currents in a magnetic field or under rotation. And you see, they are determined by state parameters, namely the temperature and the chemical potentials, and then by parameters which depend on the theory, and determine if you have an anomaly or not, which are precisely the anomaly coefficients. So DABC or BA, determining if the theory has usual anomalies like ABG type axial anomalies or this gravitational contribution to the anomaly. Now that has the effect. Let me see what I do. Yeah, let me emphasize one thing here. So if you have a system of chiral fermions, and now in the second talk, we will see such systems can be realized in laboratory experiments nowadays, in materials, advanced materials, which are called wild semi-metals. And then the anomaly, as I told you, is activated by applying electric and magnetic fields, and applying electric and magnetic fields to this sample of material in front of you. Now that's easy, that can be done. Everybody can generate an electric field, you know, you can buy it in every supermarket, you get a battery, you get some voltage, and magnetic fields are also easy. That's easy to manipulate. However, so it's easy to understand that this term does play some role for the physics of these materials. This term, however, is activated by curvature, and it's a bit difficult to manipulate the curvature of spacetime. You can't do, I mean, you can do this, but to very, very, very small extent, right? So usually we cannot make up curvatures at will. And if we can, with, you know, curvature is sourced by masses, but the masses are very small and the curvatures we can generate are too small to be measured, really. So how can this term ever play a role for the physics of materials? Well, the point is that the presence of this gravitational term in the anomaly equation is determined by this anomaly coefficient. But that's also the anomaly coefficient that tells you that there is this current induced at finite temperature, either if you rotate the sample and you get some, say, axial current, and even you can generate an energy current, which is part of the energy momentum tensor, if you apply just a magnetic field, and it goes like T squared. So if you are able to put your sample of wild matter, chiral material which contains chiral fermions, into a magnetic field and manipulate the temperature, you might generate energy currents and measure the effects of these energy currents. And in this sense, you can actually probe for the presence of this coefficient in an experimental way, without having to manipulate the curvature of spacetime, which is certainly not possible. Okay, let's see if we can really do that. Okay, let's forget this. So, wild semi-metals. This particular class of materials, here I think this is called tantalum arsenide. So now it's becoming very experimental and concrete. There is this complicated band structure. There are special points in this, what is called the Brillouin zone. Basically, what you have depicted here is momentum sliced in specific ways, and the energy levels the electrons can occupy within such a material. And 0 here is the Fermi level. So all the states are occupied until 0. And what interests us of this whole terribly complicated band structure is this little window here, and this little window here, and here. There are what are called band crossings. And these band crossings look like this. So there is some upper band, some lower band. The Fermi level here, if you're lucky, goes precisely across this crossing point, or probably slightly above or below. And then an effective low energy description. If the electrons have low energies and don't move, say, very high out to energies and far away momentum space, if they stay near these band crossing points, if you don't do things too wild to your material, then the effective electronics of these materials here can be just described by the Weil equations. There's a famous theorem originally proved in lattice gauge theory and then applied to condensed matter physics, which tells you that in such band crossings, it must always happen that in one band crossing, you get a left-handed chiral fermion, and there must be another band crossing where you get a right-handed chiral fermion. Okay. So then you can describe the effective electronics of such materials by a Weyl equation, which you apply locally to these electrons, and another Weyl equation of opposite chirality, which you apply to the electrons which sit around here. And for low energies, that should be a good description. It's very strange for high energy physicists, probably because the relativistically invariant, at least pseudo-relativistic form of the equations that describe the electronics of this material arises here as a low energy approximation. Okay, so here's a typical situation. Say, suppose the electrons, they don't sit precisely at these crossing points, but there is the Fermi level is up here. And then you apply what you have learned about chiral fermions in relativistic theory. So then this crossing point for the left-handed fermions, we call the normal ordered vacuum. That's the point where the density of states vanishes. And we do the same for the right-handed states. But they might be separated by some energy in the Brillouin zone. And this we call A05, because if you look how this enters your Weyl equation, that enters the Weyl equation precisely like a gauge field that couples to the axial charge. So here you can define a charge operator that counts only left-handed fermions, a charge operator which counts only right-handed fermions. Then you can compute the total charge, summing over right and left, and then you can compute the difference in charges, taking the right-handed charges minus left-handed charges. And they are also somewhat separated in momentum space. They don't sit necessarily at the same point. They can sit at different points, like in this previous example. And again, that enters your Teórica or Weyl-like Hamiltonian, like an axial gauge field, spatial components of axial gauge field. And then you can apply all these formulas, and what you find in equilibrium, the situation is such that what you describe as chemical potential, which is how many states are occupied above this normal ordering point for the left-handed and the right-handed. You say, okay, that's a chiral state because, you know, the Fermi surface here for the right-handed fermions is much smaller than the Fermi surface on the left-handed states. And if you just calculate the current that is generated here on these Fermi surfaces, which is very often done, then you would conclude that you get a non-vanishing current because there are many, many more left-handed fermions than right-handed fermions that can participate in generating a current on the Fermi surface. But as I told you, there is this additional term which comes, which is in a sense even more topological. And you should not forget about this. And in this equilibrium configuration, the difference in the chemical potentials is precisely the same as the difference in these energy levels, in these normal ordering prescriptions. And it turns out that both just cancel. So unfortunately, and this was, I think, sometimes thought in the very beginning, that in such materials, if you apply a magnetic field, you would immediately see a current, but that's not happening. And it's an interesting story why it doesn't happening, because there's this additional contribution to this what is called the chiral magnetic current. Okay, so the question is, can you generate somehow this chiral current? And what you have to do is you have to go slightly out of equilibrium, but not very far, into a state which is called local thermal equilibrium, which you can still describe in terms of a temperature and in terms of chemical potentials. And the way, what's also important is in these Weyl semimetals, so there is an effective low energy description in terms of chiral fermions. But of course, they are not really chiral fermions at all energy scales, because if I take such an energy band here, and I follow it up to high energies, it eventually bends around. And what started out, if I take an electron and move it over here and back down here, it starts here as a left-handed fermion, and then it turns around, loses all its notion of chirality, and comes back here as a right-handed fermion. So inside the crystal, there is a certain probability that an electron, if it just moves through the crystal, scatters on some impurity. No crystal is always perfect. There are always impurities on which the electrons can scatter. And it can scatter so hard that it's actually changes its chirality. It goes from what is called the left-handed wild cone to the right-handed wild cone. And this I have to take into account. So the electrons are really chiral electrons only up to the typical time scale on which what is called intervalley scattering occurs. So intervalley scattering allows you, changes the chirality, and chirality is only up to well defined for time scales which are shorter than this intervalley scattering time. Okay. And so you have to set up some transport equations and take this. So what you can do is, as I said, you can activate the anomaly by applying an electric field or equivalently putting a potential difference here on your vial semi-metal, put this all in a magnetic field. But you can also manipulate the temperature. So you can heat up one end of the vial semi-metal and then look how much current you get through this material. Or say how much tension would be built up in this material. So you can manipulate also the temperature, and you can build up a phenomenological theory based on this anomalous transport currents or on how such a material reacts to an electric field or a gradient, a potential gradient, like gradient of chemical potential, which is sort of equivalent to an electric field, or a gradient in the temperature. And you massage this a little bit, and you can calculate an anomaly-induced conductivity matrix, which we call sigma here. So here I've written it in a way which is the most symmetric way, where you actually look at gradients of 1 over temperature and gradients of mu over temperature and electric field over temperature. And this is a conductivity matrix, which is nicely symmetric, positive definite. It obeys the second law. You can check that it generates entropy, positive entropy, fulfills what is called the Onsager reciprocity theorem, and so on. So that's purely induced by this anomaly in anomalous currents. So one thing which is very easy to do is you can now assume that the electrons are basically free electrons, and you write down the free energy for such electrons and calculate these conductivities. They are given by these expressions, and they all depend on tau, which is the chirality lifetime inside such a material. So there are these unwieldy expressions. They are lengthy, and I have no particular insight into it, except for one thing, which I think is very, very nice. If you take this ratio of the thermal conductivity, so the thermal conductivity tells you how much energy current you generate when you apply a thermal gradient. That's the electric conductivity, which tells you how much electric current you generate when you apply an electric field. And that's the thermoelectric conductivity, which tells you how much electric current you generate when you apply a temperature gradient. Okay. And there is a law which most metals obey, which is called the Wiedemann-Franz law. This was discovered in the 19th century. And it tells you that the ratio of the thermal conductivity to the electric conductivity, and then you normalize by the temperature, is given by this universal factor, pi squared kb, Boltzmann constant over 3 e squared. E squared is the electron charge. That's not an exact law. It's a law which holds when the chemical potential is much larger than the temperature. So there are small corrections, and sometimes it's not completely. But it's a phenomenological law which many metals really obey to a few percent. And you can check that for these expressions that really holds. And what is particularly interesting or funny here is that in order for me to derive this, I needed the anomaly coefficients, and both anomaly coefficients. So these anomaly coefficients for the usual E and B anomaly, but also the anomaly coefficient for this gravitational term. And these anomaly coefficients are precisely such that they conspire in order to give me the 19th century Wiedemann-Franz law. So I find this this is of course not something which is a good derivation of the Wiedemann-Franz law. You wouldn't like to use the concepts of chiral anomalies to derive the Wiedemann-Franz law, but it's interesting to see, or amusing to see, that this law is encoded and compatible with this anomaly coefficients. You can also do this for a very large magnetic field. And the most important thing here is now the Wiedemann-Franz law becomes exact. There are no corrections to it. And that is mixed. So if you measure how much electric current you get when you apply a temperature gradient, this mixed conductivity actually goes to 0. And then you can ask, okay, so this is all stuff which, you know, is available in laboratories like batteries, electric fields, magnetic fields, etc. And these wild metals also really exist. So can one do experiments and see this? And yes, the answer is yes. So here is the first experiment measuring the contribution to the electric current due to a magnetic field in such wild semi-metal. And so this blue curve is the theoretical prediction, some sort of quadratic dependence. And the red dotted curves are the points, are the experimental measurements. There is a slight conundrum here, which is not 100% understood. This cusp here in the middle, it's some non-universal material property. Something has to do with an effect which is called local anti-localization. But okay, it's still, as far as I know, a bit under dispute what causes this really. But for a little bit higher magnetic fields, not too high magnetic fields, it follows nicely this theoretical curve. Not only this, you can also look to what the temperature gradient is doing and look to this thermoelectric conductivity. And again, you see this T-squared behavior. And then for large magnetic fields, this effect should switch off because this conductivity goes to 0. And in fact, that's also what you see. The effect just goes away for large magnetic fields. And you can also calculate, you can also measure the strong magnetic field thermal conductivity. And again, you see this typical enhancement, quadratic curve enhancement in these materials, which has a recent, more recent experiment. So all these experiments at least are compatible with this theory, and they show, at least on a qualitative, sometimes even quite quantitative level, the phenomena that you predict from this anomalous transport formula. Okay, that's very nice. And in probably another few minutes, just 2 or 3 minutes, I just mentioned that these effects might also play a big role in high energy physics. So there are these huge accelerators, famously the Large Hadron Collider at Geneva, and here's the relativistic heavy ion collider at Brookhaven in the US. I'll skip this one. So that's now we switch gears. We take the theory of strong interactions, of elementary strong interactions, QCD. This has additional gauge fields, the so-called gluons, which contribute to the anomaly, to the axial current in this form. QCD has a complicated vacuum structure, and what people do in these experiments is they take heavy ions, for example, gold ions, so gold atoms which are completely stripped of their electrons, and they're accelerated and against each other and collided against each other. And in this collision point, a new state of matter appears, the so-called quark-gluon plasma, in which the elementary constituents of protons and neutrons, the quarks and the gluons, are liberated and form a new plasma sort of state of matter. And then it might happen that the gluon fields get excited and form some non-trivial topological configuration and contribute to the axial anomaly, which would flip the chirality of the fermions in here, and will lead to a quark-gluon plasma with some sort of chiral imbalance described by axial chemical potential. And if you take into account that these parts of the nucleons which do not collide, of the ions which do not collide, they are themselves positively charged, so they generate a current, and the current, of course, generates a magnetic field. You get a very, very strong magnetic field here at the center, and so you could speculate that there's an electric current flowing. And of course, an electric current would lead to the fact that the positive charges accumulate on top of this quark-gluon plasma, and the negative charges accumulate down. And you can look for signatures in this, and I don't have time to go all through this, but that's a later experiment. Unfortunately, the signatures are not so clear. This is under heavy discussion right now. There seem to be a few % possibility of this, but it's still ongoing research on the experimental and also theoretical front. So that much to high energy applications. My time is over. Let me summarize and wrap up while I told you that these wild fermions have anomalies, which means that the symmetries or the currents, which classically are conserved, are not conserved anymore if you take quantum effects into account. You can probe for these anomaly coefficients, not necessarily only by putting the theory in electric and magnetic fields or curving space-time. Surprisingly, it's enough to probe for these anomaly coefficients by putting the theory at finite temperature and finite chemical potential and measure if there are additional contributions to electric currents or thermal currents. This can be applied and is rather well established now in the theory of wild semimetals. The signatures experiments are compatible with this theory. And there are many, many more effects, which I don't have time to go in. Quark-gluon plasma I discussed a little bit. It's supposed to be a generation, has been suggested as generation of magnetic fields in the early universe. And something which I haven't emphasized, but these currents are actually dissipationless currents because they are, I told you, chiral fermions are very stupid. They only can go in one direction. They cannot go backwards. So even if a chiral fermion hits an obstacle, it cannot go backward. It just go around it quantum mechanically. So it generates a current which is insensitive to obstacles or to impurities. And you might say, well, probably if you get better control of this, you could use this for some fancy new electronic devices, probably use it as a basis for a new architecture for a quantum computer. So all of these are thoughts that are currently investigated. Okay, thank you.
Thank you so much for this nice talk.
Thank you very much.
Is there any question from the participants? Actually, I have two questions. You said that Weidmann-Franz laws get the anomalies coefficients.
Yeah.
But we know normally.
Normally, of course, you don't need anomaly coefficients to get the Wiedemann-Franz law. I mean, that's completely independent of it. This is just my stupid or fancy way of whatever to derive Wiedemann-Franz law. I use, of course, that applies to all materials, and it's usually viewed as an indication for the fact that the charge carriers are long-lived quasi-particles, that you can think of the charge carriers as well-defined quasi-particles in a material. So basically particles which interact with the lattice and so, and they're sort of like dressed electrons. They carry the quantum numbers of electrons. They're not quite electrons, but they're quasi-particles, and they're quite well-defined. Here, I have just calculated the contribution to these conductivities, which come purely from the anomalies. Of course, in the usual material, this is a metal anyway. So, and every metal will have some sort of conductivity, right? So just by Ohm's law. But that's a part which I've actually not considered here. I've just considered only the part that is due to these anomalies. And for me, it's very amusing, not only amusing because there was also some criticism by prominent condensed matter physicists saying that this anomaly stuff violates Wiedemann-Franz law. And it's not true. Actually, the coefficients which appear, this is tied really to the anomaly coefficients for a single chiral fermion, which are strange numbers like 1/24 pi squared and 1/192 pi squared, something like this. And these coefficients conspire precisely in such a way to reproduce the Wiedemann-Franz law. So
it's very surprising. I think it's.
Well, depending on your point of view, it's very surprising, it's amusing, it's satisfying, whatever. For me, it's satisfying because some experimentalists, prominent experimentalists, say, you don't have Wiedemann-Franz law, this violates. But that's not true. It's completely, anomalies are completely compatible with Wiedemann-Franz law. What is not compatible with Wiedemann-Franz law is if, in addition to the anomalies, you have strongly interacting electrons in your material, say when the material is not described well by quasi-particles, be chiral or not chiral or whatever, but if these are not long-lived quasi-particles, then the Wiedemann-Franz law does not hold. And so there's an interesting direction in condensed matter physics where people look for so-called hydrodynamic behavior of electrons, but you cannot think anymore of electrons moving inside the material, but you have to think of some sort of fluid material that flows inside the electron. And a key signature for this thing to happen is violation of Wiedemann-Franz law. But that's something rather independent from anomalies. What I'm saying here is that even in the quasi-particle case, and even for chiral quasi-particles, the Wiedemann-Franz law holds. And that was a point which is not always appreciated. And it depends on this weird anomaly coefficients. Yeah, which that's indeed at least amusing, I would say. Yeah.
And my other question is about what calculations you showed in the previous slides in 5 dimension. It's here, yes. The other side.
Let's put
maybe the
yeah.
next slide.
Yeah, yeah.
But these calculations, actually, normally we know how to look like chiral separation effect, chiral magnetic effect, and we already know the coefficients. And this method, the parameters you defined mu and the other f nu comes from what we already know. I mean, you define effective action and then calculate the currents.
Exactly.
But it's the general form, and you define the mu chemical potential and the other parameters depending on what we already know, the chiral magnetic effect, chiral separation effect coefficients, right?
Well, every good calculation in physics you can only do after you get the right result. So there is a lengthy story to it, and I tell you this. It's more historically. So the first thing is this. Okay, so basically all the previous calculations, first calculations of chiral magnetic effect, forget either about this term. Most of them forget about this term, or some exceptional ones. They forget about this term, and they only calculate this or that. But it's important that both terms are there. And this has led to some confusion. For example, people said, oh, you get a current if you just apply a magnetic field and you have this mu5. And it's not true. You don't get it because you have the cancellation between these two terms.
And this method is more general because.
And this method is general. It's general. It shows that you get both terms for the chiral magnetic effect, right? But on contrary, it also shows that you don't get two terms for the chiral separation effect.
Okay.
So there's a difference between chiral magnetic and chiral separation effect. And this is that was not always so appreciated. And therefore, this method shows that explicitly, because once you generate a boundary term, and in the other calculation, you don't generate that boundary term. And that boundary term makes all the difference if you see a current or you don't see a current. And the other thing is that in the usual way of viewing things, the transport that is induced by the chemical potential looks very different from the transport that is induced by the temperature. And that the temperature effect is related to the presence of the gravitational anomaly is not, sometimes it's criticized. It's said this is crazy because there is no curvature. Obviously, there is no curved space-time in a Weyl semi-metal. I mean, no experimentalist so far can curve space-time so much that he could see this term in a Weyl semi-metal. So it's irrelevant. And the opinion was that this particular anomaly is completely irrelevant for all transport. However, from this effective point of view, there is absolutely no difference in the treatment of this term, which contains the curvature terms, and then you encode the temperature in the geometry, or For this guy, where you have just chemical potential and gauge fields, it's exactly parallel, and the same principles at work, and you see explicitly that the anomalies in terms of these Chern-Simons terms give rise to these currents, and both derivations for the mu terms and for the t terms follow precisely the same principles. Now, I'm not so clever to invent this by myself. This is something that comes out basically from what is called the ADS-CFT correspondence. So in the ADS-CFT correspondence, this is precisely how you do it. This is how we actually found it and how we got convinced that really this gravitational anomaly plays an important role in the transport through these temperature terms. But you can make, because the anomalies are universal and independent of the coupling, so ADS-CFT is only valid for extremely strongly coupled large N theories, etc. But because of the universality, there should be a way of calculating and doing this calculation completely independent of ADS-CFT. And this is sort of my motivation for presenting it like this, doing something which is inspired by ADS-CFT, but is not ADS-CFT, but is completely general and applicable to any theory that has this type of anomalies. And the nice thing is it highlights various subtle points in the story which has been overlooked very often, like the cancellation between these two terms. And everything's automatic in this approach. It comes out.
I'm wondering, can we calculate the local polarization effect from this method?
Yeah. So, okay, that's a difficult question. So spin polarization, you say, right? Now, spin. I'm not the right person to talk about spin, because you see, my theories are nice, massless, and fully relativistic. And you can convince yourself very easily that spin is not a conserved quantity in a relativistic theory. There is no way you can make that conserved. And the simplicity on the spin operator doesn't commute with the Dirac equation. Usually we don't consider spin as a good observable in relativistic physics. Now, that means, for example, that I do not introduce necessarily spin chemical potentials or anything like this. These are highly ambiguous concepts. It has to do with this thing that the energy momentum tensor is not uniquely defined. You can always do this, what I call pseudo-gauge transformations, and add some derivatives of the spin current. You can always set the spin current to 0 by pseudo-gauge transformation and all of this complicated stuff. Now, theoretically, this was my excuse until like a year ago or 1.5 years ago or so, that never look at spin. However, experimentalists are very nasty people because they actually measure spin. And so one has to think about how to get the handle on spin. And there's a lot of activity on that. But I have to, I have told you now basically everything I know about this. And this is mostly my doubts about how even to address the question. So let me keep it at this. I don't think these anomalous transport theories shed any light onto spin polarization. Well, one has to be more careful because, at least for Dirac fermions, it is true that the axial current is not the spin current, but it's the Hodge dual it's the dual to the spin current. So there is some notion in this anomalous transport story, which has to do with spin, which is the axial current for Dirac fermions. If it can be used to calculate spin polarization at heavy ion collisions, I think there have been some attempts. I don't know. But it's probably worth looking at it. But there are many different schemes which look to that.
Okay. Thank you so much. Is there any other questions? Ayman?
Not really. After your very technical question and precisely. Okay, I think yeah, I don't have some question
Okay.
related to.
Okay, thank you so much for this nice talk, and
Okay, thank you again for the invitation.
Thank you for clear presentation.
Okay, thanks. Good.
have
See
a
you,
nice
bye.
day. See you.
Thank you. Nice day. Bye.
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 Let's stop this.